Okay, here's our next example for finding the intervals of increasing and decreasing. First thing I want to point out about this example is that your function's actually not defined at x equal -1, because if you were to substitute -1 into this function, then you would have 0 in your denominator, so obviously there's some kind of discontinuity. Now, this is actually going to end up, the -1 is going to end up showing up after I do my derivative anyway, but you can have, your function change from increasing to decreasing or vice versa on either side of -1. So when you do your sine graph, you would need to make sure that you do put -1 on your sine graph. And like I said, it's actually going to end up showing up when we do our first derivative by chance anyway. All right, so taking your first derivative, of course, this is going to require that we do the quotient rule. So we'll have low d high minus high d low over low low. All right, so if you distribute your 2x, then you're going to have 2x squared plus 2x, and then this would be minus x squared. So combining your like terms, you'll have 1x squared plus 2x for your numerator. Now you can factor out an x on the top, and you could go ahead and do a step of doing that. I'm just going to wait and deal with it on my next step. Now, getting your critical numbers, and just as I stated a while ago, you just find out what makes your first derivative equal 0 and also what makes it undefined. Now, when you're dealing with a rational function as you are here, this is going to be, this function or this first derivative will be equal to 0 when your numerator equals 0, and then it will be undefined when your denominator is equal to 0. So set your numerator equal to 0, and set your denominator equal to 0. Okay, so solving this, you would factor out an x. So therefore, you'll have x equals 0 and x equal -2. And I went ahead and left this to the second power, but actually, you would not have to even worry about the second power to solve this or to find out what makes this undefined. You would actually only have to worry about just the x plus 1, because the fact that this is equal to 0, your first step would be to take square root of both sides, but square root of 0 is still just going to be 0. So that's why really when you're dealing with your denominator to the second power, you could ignore the second power. All right, so we're going to end up with x equal -1. So this is where I was talking about that this, where we stated back up here that the function was not defined at -1 to begin with. There was a discontinuity. It happens to show up down here as well. Sometimes it will, sometimes it won't. All right, so when you're doing your sine graph, okay, so marking these off on your sine graph, of course you'd have your -2, and then your -1, and then your 0. And then we need to pick a test number in each of these intervals. Okay. Again, we're not all going to pick the same test numbers, just as long as you're picking a value that would fall within that interval. And you're going to substitute these, remember, into your first derivative. So you can go right back here to this step. This would be where I had simplified my first derivative. All right, so take the -3 and plug this in. Of course, I'm just going to leave that up to you to do the calculations there. But this is going to give you something that's going to be positive. And then if you substitute in the negative 1.5 into your first derivative, you're going to get something that's going to be negative. And then between the negative 1 and the 0, I've got negative 0.5. So you substitute this into your first derivative, you're going to get another section that's negative. And then last, if you substitute in 1, then you're going to get something that's positive. So that would mean this is a section that's increasing, decreasing, decreasing, and increasing. Okay, so writing out what we have here for these intervals. All right, so you're going to increase. Of course, this is starting over here on the left, so this would be negative infinity to the negative 2. Now you also have an increasing section that would go from 0 to positive infinity. Now, decreasing, since these are side by side, sometimes you can actually lump those sections together and treat it as if it were all one interval, but sometimes you can't, and that's just going to depend on the situation that you have with this number, in this case the negative 1 that separates these two sections. That's why it was important back up here to realize that x can't equal negative 1 to begin with, because that causes the original function to be undefined. So because that's it's not part of the domain, because if you remember, domain is your x values, and in this case negative 1 has to be left out of your domain, you have to write this as if it were two separate sections, because this is not part, your function's not defined at negative 1 to begin with. So we would state that you're decreasing from negative 2 to negative 1, and then from the negative 1 to the 0. And just like I told you a while ago, you can always take your calculator and graph your original function and just see if what you have here matches up with what you're seeing on your calculator. Okay, so actually just adding a little bit to what we've already been doing, we have what's called the first derivative test. And this is actually going to help us determine where do we have maximums and where do we have minimums. And you can actually get that from the sign graph that we've already been doing. So like I said, we're just going to do what we've been doing, but add just a little bit to it. So as it states here, if your first derivative changes from negative to positive. Now, if your first derivative changes from negative to positive, that's going to mean that it's decreasing and then increasing. Because remember, that's what we determined, was those sections that were negative were decreasing and those sections that were positive were increasing. So if your sine graph changes from negative to positive, then you're going to have a minimum point. Then if it changes from positive to negative, which means it's going to change from increasing to decreasing, then that would be a point in which you would have a maximum. And of course, if there's no change at all, then there is no max or min. Okay, so let's take this one. So again, we're still going to find out where is it increasing, where is it decreasing, but then we're also going to find those maxes and mins. Okay, so we got to start off first of all by getting our first derivative, and this is a 4. Of course, there's those random dots that I've talked about before that it prints off for some reason, but this is x squared minus 4. All right, so your first derivative, you'd have to start off with your power rule, so you'd have 2/3 times your function to 1 less power. So that's going to drop to a negative 1/3. Then you have to apply the chain rule and take the derivative of the inside. So the derivative of the first term would be 2x, and of course the derivative of 4 is just 0. All right, so simplifying this, you would need to move the parentheses, since it's a negative exponent, move it to your denominator. So you'd have the 2 times the 2x. So that means I'll have a 4x for my numerator, and then I'll have 3 times the x squared minus 4 to the 1/3 power as being my denominator. Okay, so let's work on finding those critical numbers. Where is my first derivative equal to 0, and where is it undefined? So to find out where it's equal to 0, that would come from your numerator. So you would do 4x is equal to 0, therefore x would just be equal to 0. Now your denominator, if you remember what I mentioned to you a while ago, is the power is actually not going to affect anything here, but having the 3 multiplied times it is not going to affect anything either, because just imagine you're going to say that this is equal to 0, and your first step's going to divide by 3. It's still going to be equal to 0. So you can just take the x squared minus 4 and not worry about the times 3 and the 1/3. And of course you're going to use your square root property, so you end up with x is equal to plus or minus 2. Alright, so this will be the numbers that I need to put on my sine graph. So I would have -2, 0, and +2. And then you got to pick your test numbers. Okay. Now remember, these test numbers are going to be substituted into your first derivative. Okay, I don't have the answers for this one already calculated, so I'll just kind of have to do this as we go. Alright, if I put a -3, that's going to give me a negative on the top. But if I put a -3 down here, then that's going to give me a positive. So I'll have a negative over a positive, which is a negative. Okay, then if I substitute in -1, of course that's going to give me a negative on the top. But now substituting down here, of course that's going to give me 1 minus 4, which is a -3, but this would be a cube root, and you can do the cube root of a negative. The cube root of a negative is just a negative. But like I said, just type all that in your calculator instead of trying to do any of it in your head if you want. But I have a negative over a negative, so this is going to be positive. Now if I put in +1, that's going to be a positive over a negative, which is negative. And then if I put in 3, that's going to be a positive over a positive, which is a positive. Okay, so as far as increasing and decreasing is concerned, let's go ahead and describe those intervals. Of course, this is going to be decreasing, increasing, decreasing, increasing. Okay, so decreasing would be -infinity to the -2. I'd also decrease from 0 to 2. And then increasing would be -2 to 0, and then from 2 to infinity. Okay, now here's where what they call first derivative test comes in as far as finding the extrema with the maxes and the mins. So if you remember what I stated, I said if it changes from positive to negative or negative to positive, that's when you're going to see these extrema. And if your graph is decreasing and then it changes to increasing, that would be a section that's making what I refer to as a valley. So that means here at -2, you would actually have a minimum value. Then if you go increasing and then you get here and you have to change to decreasing, that's making a hill. So this is going to be a max. And then here I decrease and then I turn and increase, so that's making a valley. So this would actually be another minimum. Now these are actual points on the graph, like what is the point that's the max, what is the point that's the mins. So you actually need to locate the whole ordered pair in this case. So start by substituting -2 because this is where you're going to have a minimum. Substitute this back into the original function because you're locating an actual point on this function. So when you're doing this, don't plug into the first derivative like we did here. You go all the way back to the original function. Alright, so if I substitute in -2, then that's actually going to give me 0, so that would be the point -2, 0. And then if I substitute in 0, again I'm going back into my original function, that's going to give me -4 to the 2/3 power. So you actually could write that as cube root of 16, because remember your bottom number is your root, your top number is your exponent, so -4 squared is the 16. So this would be the ordered pair 0 cube root 16. And then I have the +2, which I also have a min there. So if I were to substitute +2 back into the original function, again I'll get 0 there, so that would be the 0.20. So this was a min, this was a max, and this is a min.